Okay, let's continue. We have seen the magnitude response of one case, and that single case was, in fact, we have seen two cases, sorry about that. One of them was this first order system with only a single pole, and the magnitude response was a low pass behavior, as we can see here. And the second example was this, which was an all pass filter. Now, a second order system is interestingly important for a number of applications. So we have to briefly see things about this second order systems. But it will be quick, unlike some other books or some other literature which pays a lot of attention to these second order systems, as if the whole world is consisting of those. But it's in a sense correct, because a second order system is thinking of the first derivative and the second derivative. And in the universe, in the physical reality, we have mostly those two forces. One of them is the acceleration, the other one is the velocity. So it makes a lot of sense. But for us, mathematically, it's just a second order system, and it's not much different from other higher order systems for our case. A second order system is in the impulse response notation. It looks like this: m times e to the c1t minus e to the, oh, what's happening? E to the c2t times u of t. The impulse response, therefore, induces two separate decaying exponentials. So that's why it is having two poles, and that's why it's a second order system. But if those two poles are conjugates of one another, just imaginary poles, in other words, or complex poles with imaginary parts being reciprocals of one another, that would induce a sinusoidal oscillation as well. So, but we will take a look at those things later on. Let's first find the Laplace transform of this. But I'm not going to find the Laplace transform in this particular representation of h of t, but eventually I will convert many of the outputs to, why is it happening? To some new parameters. One of them is omega n squared divided by s minus c1 times s minus c2. One of them is this kind of a notation, because the poles, as we know, will be at c1 and c2. So it's clear how we can come up with this. Or omega n squared divided by the denominator being in an open form of second order polynomial, quadratic polynomial of S. Like this. Now, as you see here, we are experiencing some notation problems, because in the first notation, we only have m, c1 and c2, whereas now we have omega n in the square form. c1 and c2 is here, but in the after being expanded, now we have some different things, like omega n being here and here and here, together with a lambda. So what are these? It's not very much complicated, fortunately. M come on, m is equal to omega n, I will erase it later, to lambda square minus 1, and C1 and C2 are the original damping factors, which are the pole locations. C1 is equal to minus lambda omega n plus omega n square root of lambda square minus 1, and C2 is equal to minus lambda omega n minus omega n square root of lambda square minus 1. These lambdas, omega n's, etc., they are there because of historic reasons. People have been working on these second order systems a lot, and they are just inventing some notations to put particularly with some certain names given as parameters. For example, lambda over there. Lambda is related to the second order filter's bandwidth, and therefore the quality factor you may remember from circuits. So this is the second order system layout that we have. And the situation or the position of the poles for these second order systems will be also important in your second semester control systems courses according to this. Suppose that lambda is greater than 1. If lambda is greater than 1, all right, lambda square minus 1 here and here will be positive, and square root of that positive number will be a real number, a real positive number. So around minus lambda times omega n, which is somewhere here, plus and minus of those of this will make the positions of the poles. So we will have a pole, let's say here and here. One of them is, this is for lambda greater than 1. This is the point where it's equal to minus lambda times omega n. And this is this center point plus something, and this center point plus minus something is the other one. So we have these and these. I will try to erase this. Okay. And this is for lambda greater than 1, the real axis and the imaginary axis. So the poles are on the real axis. There's no problem over here. And it seems to be a low-pass filter. A low-pass filter. Why? Because if you put an omega value here, you see that the distance from this pole and the distance from this pole will be minimum when the frequency is pulled all the way down to 0. And as you proceed to plus infinity or minus infinity, the distances from the poles will increase. So in general, it will decrease the magnitude response towards the tails. That's why it's a low pass filter. But this is only happening as lambda is left greater than 1. So let us have a knob and let us reduce it a little bit, and let's make it close to 1. When it gets close to 1, this thing becomes 0. If it is 1, for instance, this is exactly 0, this is exactly 0, and C1 and C2 will be at minus omega n, minus 1 times omega n. Lambda is equal to 1, remember that. So from here, as lambda approaches to 1 plus, we will have like two poles, multiple poles, at around minus omega n. So it's like these poles are moving towards one another. We had two poles and they are moving to one another, and they meet at omega n when lambda is equal to 1. Okay? They are moving and they meet at minus omega 1. Then what happens? Then let's say that lambda is less than 1. If lambda is less than 1, we are starting to experience problems. If lambda is less than 1, between 0 and 1, in other words, lambda square will be less than 1, and less than 1 minus 1 will be a negative number. So inside the square root, I will have a negative number, and the square root of that negative number will give me an imaginary number. So j times something times omega n, and lambda is between 0 and 1, let's say. The real part is at minus lambda omega n, and the imaginary part is determined by this plus and minus form. So it will be in the conjugate forms. Between 0 and 1, it will be like this. Lambda will be small, so minus lambda times omega n will be somewhere nearer to the j omega axis. But it's not, sorry about this. The pole will not be there. The real part of it will be there at this point, but the pole will be here and here, where this is minus lambda omega n, and this much is the imaginary part that we have. And if lambda is exactly equal to 0, then it will be 0 minus 1, which is minus 1. Square root of that will be j, the imaginary j, and I will have omega n only, and lambda will be equal to 0. So at omega n and at omega n plus, sorry, at 0 plus j omega n and 0 minus j omega n, I will have two poles. So these poles are, as you approach to 0, they will come here and here exactly, which is omega n and minus omega n on the imaginary axis, on the j omega axis. As you approach to 0. So what is the thing that is going on? We can plot them all together like this. We started by, please, we started by two poles. They merge to one another. Okay, they come together. They make the same pole at the same location of minus omega n. And from there on, one of them moves up, the other one moves down, like this, in conjugate pairs, and they first move until is omega n and minus omega n. This is the j omega, this is the sigma axis. Okay, they merge and then they split and move closer to the j omega axis, and they end at the j omega axis when lambda is equal to 0. The range of lambda that we are dealing with is between 0 and infinity. So this is how things behave. They are separated along the sigma axis at first. They come together as lambda approaches to 1. When lambda is equal to 1, they meet. And then afterwards, one of them goes up, the other one goes down. and they bend towards the j omega axis, and they stop at the j omega axis when lambda is equal to 0. This kind of a motion or the trajectory of the roots is known, you will see that again in the next semester in control systems. It's known as the root locus. The locus means trajectory or the location. It comes from the term location in English. Root location. The root locations are moving in this along this trajectory for second order systems. For higher order systems, of course, or for other kinds of systems, we have other root locus. But root locus is not our concern now. I'm just giving you this information as some side information where you can benefit in next semester's control systems. So when you see root locus, you will have to think of the roots of the system. And as you change a parameter, let's call it lambda, by changing lambda, they are moving. And those motions will help you design your systems. For instance, when lambda is set to be greater than 1, the system becomes a low-pass filter, whereas if lambda is between 0 and 1, since the roots split into two conjugate pairs, they become band-pass filters. Okay. There are several other things that we can talk about. For example, the bandwidth is equal to 2 lambda for the second order system, whereas the quality, oops, that's not Q, it's phi. The quality factor of this filter is known as 1 over the bandwidth, which is 1 over 2 lambda. So the choice of lambda will also help you indicate how sharp you are. Notice that when lambda is equal to 0, you meet along the j omega axis, and the pole appears exactly on the j omega axis here and here. And they are extremely sharp. You remember the three-dimensional shapes that I have shown you? They were very sharp. And the quality factor of those very sharp, very narrow bandpass filters is essentially 1 over which is infinity, as you see, because Q is 1 over 2 lambda. Therefore, the quality factor is essentially infinity when lambda is equal to 0. So these are some notes about the second order systems. I'm not a big fan of these second order systems. There are even some courses and lectures dedicated to these second order systems, but for me, they're just a numerator of S over a denominator of S polynomials and nothing more than that. So I'm not going to spend any more time, and I will jump to the properties of the Laplace transform. We have already seen a lot of properties anyway, but let's list them out. The first is linearity, of course. And that's simple. A times x1 of t plus b times x2 of t will make a Laplace transform that is equal to a times b times x2 of s. That much is clear. But remember that our Laplace transform business is only marginally related to x of s, but it's more like we are dealing with the region of convergence. So what is happening to the region of convergence is the critical thing here. And the way that the book notates the region of convergence for these is something like this. They say the region of convergence includes R1 intersection with R2, where R1 is the region of convergence of this, and R2 is the region of convergence of this. So we have two regions of convergences related to x1 and x2. Clearly, we need to have the intersection of those things. I would expect that the region of convergence is indeed just equal to R1 intersection with R2. However, it's not. It's only including. It's a superset of that. It may be equal to this R1 intersection R2, and in a majority of cases, 99% of the cases, it's just intersection of R1 and R2. But there may be some points where, when you add this and this, there may be some pole and zero cancellations. And if a critical pole is canceled, which describes the region of convergence, then we don't really have a bound of that region of convergence with respect to that pole, because it's canceled in this summation. It may happen, so you have to always check the region of convergence. And the example, or actually a counterexample of an intersection result only, is the following. X1 of S is, I'm already giving it in the form of the Laplace transform, no big deal. 1 over S plus 1. And the second X2 of S is equal to 1 over S plus 1, S plus 2. Okay. And here, R1 is described as real part of S is greater than -1. And R2 is also described as real part of S is greater than -1 again. Because we have two poles, one of them is -1, the other one is -2. It's to the right of -1 intersection with to the right of -2, which is to the right of -1. So we have these two poles, two Laplace transforms, and their regions of convergences tell me that it is to the right of -1. However, if you have a further x of s, which is defined as x of s minus x1 of s minus x2 of s, okay, and when you do that, you will find it to be 1 over s plus 1 minus 1 over s plus 1 s plus 2 will be equal to 1 over s plus 2. If you do the algebra, you will find this. And the region of convergence is real part of S is greater than -2. So as you see, this is not equal to R1 intersection R2, because R1 intersection R2 was telling me that it should be real part of S greater than -1. But now it is to the right of -2, which is a larger region of convergence. Like this. One of them is at -1. The other one is at -2. To the right of -1, as you see, is a smaller region of convergence, but to the right of -2 is a larger one. So it includes this one includes this one. That's why I have indicated it's like this. The region of convergence includes R1 intersection R2. It doesn't have to be exactly equal to their intersection. Which is also another way of saying that the regions of convergences are something that you have to just evaluate separately and even individually. You cannot really depend on a rule which is saying that it's just in their intersection. No, that's not true. It includes their intersection, but it is something else that you have to find. Now the second property, we will do as much as we can, and then we will just stop. The second property is shift in S domain. And this is versus, of course, multiplication in time by exponential. So what do we really mean? If x of t has a Laplace transform of x of s, where the region of convergence is, let's say, R, a region, then e to the s0 t, which is the exponential that we multiply, okay, times x of t, so that we make this kind of a multiplication, we can clearly find from the integration formula that this makes x of s minus s0. Okay, so what is the new region of convergence? According to the notation of the book, it doesn't really make much sense, but I will try to explain it from examples. It says it's the region that is shifted. This plus is therefore not a summation because we are really adding regions. So it makes a shift to the region by an amount of related to the real part of S0. So the region is either shifting right or shifting left or up and down. But up and down shifting does not change the region of convergence. That's why I'm putting a real part of S0. The stripe that we draw, it's irrelevant where the pole was. The pole may be moving up, moving down, but the region is still the same. The region is determined by the real part of S0 only. So, for example, if you had two boundaries like this, and in between, let's say it's the region of convergence, with respect to the real part of S, it may be, let's say, moving to the left, both of them moving to the left to make some new region boundaries. And now your new region will be like this. So I think the correct way of putting it is, for example, if this is R2, then this new point here will be R2 plus. Now, an interesting thing that you can observe about this kind of a relation is when this S0 is purely imaginary. For example, it's equal to j omega 0. J times omega 0 is an imaginary value related with omega 0, of course, but it has no real part. So if you multiply anything with e to the j omega 0 t, then the region of convergence actually does not change because the real part of S0 is 0. So if you oscillate, modulate, in other words, your signal, then the region of convergence related to the corresponding Laplace transform does not really change. The new poles will be, of course, somewhere else, but the poles will be moving only up or down, okay, depending on the value of omega 0. And since the poles are moving vertically, the boundary that is related to the real part of that pole is not really changing. The boundary is not affected. The poles are just moving vertically if S0 is equal to j times omega 0. That is some critical observation that you have to always remember. Another one, let's make it black. The third property is time scale. So x of a times t, I'm scaling the time t by a, will have a Laplace transform, which is really very much similar to the Fourier transform, 1 over a times x of capital X of s over a. You may remember that when s is equal to j omega, this is exactly the same property that we had for the Fourier transform. And then the region of convergence works like this. And I cannot really find a way to notate it, so I have to give you an example for that. S over A will be the location of your new pole. So if there is a pole at let's say R1, and if there is another pole at let's say R2, these are the two poles on the S plane. For x of t, from here we will have a new set of poles, and one of them will be at a times r1, and the other one at a times r2. So if the previous region of convergence was between r1 and r2 like this one, after the time scaling, the new region of convergence will be between a times r1 and a times r2. Okay. You can think of it because of this. S over A is equal to R1 will be your new pole. Therefore, S is equal to R1 times A is the new pole. A times R1, as you see here. Or A times R2 similarly is here. So the new poles are just scaled according to whatever the value of A is. Please ruminate by yourselves, think about it, contemplate a little bit. What really corresponds to A is something larger than 1, and A is something between 0 and 1, less than 1 in magnitude, in other words. If A is larger than 1, x of A times t is essentially squeezing, shrinking down the signal and making it a shorter signal. And shorter signals usually have better convergence. Okay. Therefore, the poles that I would expect are farther away from the j omega axis to make sure that the j omega axis is essentially included in the region of convergence. So the poles are farther away from the j omega axis for A large. But if A is small, then the poles are approaching dangerously near to j omega axis, which is a critical issue about the convergence, because j omega axis must be included in the region of convergence. So we want the poles to be as far away from the j omega axis as possible. So if A is a small number, x of A times t is actually widening your, stretching your signal, making it a longer signal, and longer signals are more difficult in terms of convergence because it's easier to integrate, or it gives a smaller value to integrate if you integrate a shorter sequence, for example. Think of it like that. I think that's enough. Yeah, these three properties are enough for today. We can stop at this point. We will continue with a few more properties. Some of them will be quite important in, again, solving problems. But regarding the problems, knowledge of the Fourier transform is very helpful for these, because as you see, S is equal to j omega would really correspond to the Fourier transform. So if you want to take the inverse Laplace transform of something which you don't know, as long as the region of convergence includes the j omega axis, just say that S is equal to j omega and try to look at the inverse Fourier transform instead. That will help you to understand the relation. So if you don't know the Fourier transform, but if you only know the Laplace transform, it would be a little bit more difficult for you to solve even Laplace related questions. Okay, now I will stop the recording. I can ask you a few, I can wait for a few questions from you if you wish, but after